Paracetamol is a medicine commonly used to relieve mild pain. It's a painkiller. Traditionally, paracetamol has been made industrially in a three-step synthesis from phenol. Phenol is a benzene ring with an OH and alcohol group on it. And here in step 1 that I need the mechanism for, it's had an NO2, a nitro group, bonded to it. The way that you get groups bonded onto the ring is you have a look at the group and you make it plus charge. So that's been NO2 plus, and that gives a reason then for the ring to attack the plus charge on whatever species is then going to join onto the ring. So I need to make NO2 plus. So the way to make NO2 plus, I know it doesn't ask it in the question here, but we might as well know. Nitric acid HNO3, sulfuric acid H2SO4, you need to remember that, and you're going to make NO2 plus. That's easy to remember because you look at the group NO2 and you make it plus charge. The plus is actually on the N, but you won't get it wrong by putting it anywhere around it. It is actually on the N. What else will I get made? Well, unsurprisingly, I'm going to get some waters. I've got some H's and some O's, so I'll make some water. And then what's left? I've got 2 H's on the right, I've got 3 on the left, so H, an S on the left, not used yet, an S on the right, 7 O's, 1, 2, 3, I've got 4 O's in this. I've made a plus, so I need to make a minus. This is called a nitronium ion, NO2 plus, by the way, water, and hydrogen sulfate. Now the mechanism looks like this. So electrons come from the ring and attack this plus charge on the N. The plus should really be on the N, and the N bonds to the carbon then. So this is an electrophile electron pair acceptor, and it replaces the H that's on there. So remember, there's unseen H's on each of the carbons here. This is a skeletal formula, and there's unseen H's. So this is an electrophile electron pair acceptor replacing H. So this is going to be electrophilic substitution. Just to finish this off then, electrons given away from the ring, that's why it's a plus charge. We break the ring temporarily and we draw a horseshoe. I prefer if that diagram there had a closer horseshoe, so the gap was a little bit tighter towards this carbon that's got the NO2, and the electrons go through the gap and into the ring then from the H. The H is then released as H plus because electrons have gone away from it, so it's broken off and it's a plus charge, and the plus charge then balances out beginning and end, and the NO2 group then is added to the ring via electrophilic substitution. Complete the equation for this one. Well, I've replaced O's with H's. So the easiest way of replacing O's with H's or adding H's to something is to add hydrogen. Add hydrogen. Here, unsurprisingly, the hydrogen replaces the oxygen, so I've added some extra hydrogens. I'm going to make some water, fairly obviously, and I'm going to balance it here. Two O's, 2 O's there, 2 waters, 4 H's, 5, 6 H's, everything else remains the same, 6 H's. Incidentally, you need a nickel catalyst here, and the mechanism type when you add hydrogen is called hydrogenation. So it's a hydrogenation mechanism. You don't need to know the exact mechanism for it, but it's called hydrogenation. And hydrogen, when you add hydrogen to anything, it's called hydrogenation. You need a nickel catalyst. And that's the easiest way to replace O's with H's, or just to add H's to something like CNs to make amine groups, primary amines. In theory, after ethanol, chloride or ethanoic anhydride could be used in step 1, complete the mechanism. So this is something called additional elimination. When you get an acyl chloride, that's a group with a C double bond OCl, then you get additional elimination. A special kind of mechanism. R can be any group you want. So I've got an NH2, an amine group, with an R, which can be anything. So it attacks the lone pair of electrons on the N, attacks the C, and the double bond breaks and goes on to the O. The next stage is that the NH2R, the NH2R bonds to that C. So I've got now a bond where the N has used its pair of electrons to bond to the C. The electrons from the double bond have gone on to the O, so now it's got a single bond. I've drawn the pair of electrons there from the bond on the O, and it's minus because it's had an electron and an arrow go towards it. Now, in the next step, next part of the mechanism, you need 3 arrows. The Cl is broken off at this point. Electrons go from the bond onto the Cl. The Cl is electronegative anyway, so withdrawing electrons towards itself. So no surprise the electrons break from the bond and go into the Cl. The lone pair of electrons, remember an arrow can only come from a lone pair or a single bond, double bond or a ring. There's only 4 places it can come from. It can't come from that minus. If you draw an arrow from that minus you'll get it wrong. It's coming from the lone pair and reforming this double bond. So in additional elimination the double bond breaks but then reforms in the next step. And I've got to get rid of this plus charge on the N. Remember the N has got a plus charge because it's had electrons go away from it. So the minus is formed here. I need a plus charge at the same time and the plus charge is on the N. That N has got too many bonds. It can only have 3 bonds. So I'm going to break an H off and move the electrons onto the N. The electrons are minuses, so that'll get rid of that plus on the N and break the H off as an H plus. So I'm going to get this formed, C double bond O, CH3, C double bond O, the Cl has gone, the N has now become NH because one of the H's is broken off and there's the R group still on there, and the plus charge and the minus charge have disappeared because electrons have gone away from the O, that's removed the minus, and electrons have gone onto the N, that's removed the plus. I'll also get H plus and Cl minus. I'll get HCl formed as white steamy fumes. In practice, ethanoic anhydride is used in industrial system synthesis rather than ethanol chloride. Give 2 reasons why ethanol chloride is not used in the industrial synthesis. Well, in the MARC scheme, they only allow 2 things. It's corrosive and dangerous. Ethanol chloride is corrosive and dangerous. I've said it's dangerous. It gives off white steamy fumes of hydrogen chloride gas which dissolves in your lungs, makes hydrochloric acid in water or in moist tissues such as your lung, and will dissolve your lungs. A very, very toxic gas. However, not in the MARC scheme, but the real reason, incidentally, that they don't use it in industrial synthesis is because ethanoic anhydride is more expensive. It's less expensive than ethanol chloride. So ethanol chloride, corrosive and dangerous, burns the skin. Dangerous, makes hydrogen chloride white steamy fumes, which are toxic, and also ethanol chloride is more expensive than ethanoic anhydride, and that's one of the main reasons they actually use it in industrial synthesis, to try and save some money. In step 3, other aromatic products are formed as well as paracetamol. Draw the structure of one of these other aromatic products. Well, let's go back and have a look at step 3. Step 3. So the ethanol chloride is bonding to that N. So the lone pair of electrons on the N is bonding to the COCl, the C of the COCl in additional elimination reaction. However, there's a lone pair of electrons on that oxygen as well, so there's no reason why the oxygen couldn't bond to the COCl group, and this could form an ester. I'll show you what I mean here. So there's a lone pair of electrons on the O, and this is my ethanol chloride, so the lone pair of electrons can bond to that C and it will release HCl. So I get HCl released here in a condensation reaction. Remember, a condensation reaction is where small molecules such as water or HCl are formed. So a condensation reaction is not just making water, it can make small other gaseous molecules, other small gaseous molecules like HCl, and therefore I'm going to get an ester formed here when HCl is released. So the O lone pair of electrons will attack that C, and then you get additional elimination mechanism, and it forms this chemical here. Tricky one here in the second step of this reaction. Hydroquinone, this one, reacts with ammonium ethanoate to form paracetamol. Complete the equation for the second step. The first thing is the ammonium. Ammonium is NH4, eth is 2 carbons, ethanoate is an ester. So I've got CH3, CH2, C double bond O rather, O. So CH3CO and then an NH4. That's ammonium ethanoate. That's the hard bit of this question. CH3CO, 2 carbons, eth. O8 is an ester, C double bond O, and NH4 is ammonium. And then all I've got to then do is, I think it's fairly obvious what's going to be formed here. I seem to have lost it. Some H's and some O's. I've got too many H's and O's in here. I've not got enough here. So it looks as if I've got to release some H's and some O's because the H's and O's have disappeared. I'm going to make some water, and you can balance it by counting up the H's and O's, and you need 2 H2O. Tricky question that, but once you've got the ammonium ethanoate, and you've worked out there's probably water formed because there's O's and H's that aren't accounted for, that are on the left and not on the right. You can balance it and mix some water, but difficult, that one. 8.7. Calculate the mass in kilograms of hydroquinone MR 110 needs to produce 250 kilograms of paracetamol. Well, first of all, I need to find out what paracetamol is and hydroquinone and work out the MR of paracetamol. So I've got paracetamol here, and I can add up the MR of that with 1, 2, 3, 4, 6 carbons in the ring, that's 12, 4 hydrogens on the ring that are unseen, an oxygen which is a 16, a hydrogen on the OH, an N is a 14, a 1, a 12, a 16, a 12 and 3 ones, and it will come out at 151. So now I've got 250 grams of kilograms of paracetamol. Now I've skipped a step here. I could turn kilograms into grams by multiplying it by 1,000, but then when I get my amount of hydroquinone in grams, I'm going to have to take it back to kilograms by dividing by 1,000, so I can convert my kilograms into grams, and then when I get my answer in grams, convert it back to kilograms. So I can just leave it as it is, actually. So I'm going to choose to leave it as it is. So moles of paracetamol, moles is mass divided by MR. Actually, no, here I've multiplied it by 1,000 to get it into moles. I could have avoided the 1,000 bit, but I have done that, sorry. 250 divided by 1,000, so I've converted my 250 kilograms into grams by multiplying by 1,000, divided by the MR, and worked out the moles of paracetamol. 1655.6 moles. That equals the number of moles of hydroquinone used, because 1 mole of hydroquinone makes 1 mole of paracetamol. So I've got the same number of moles of hydroquinone used, and then moles is mass divided by MR. I've got the MR of hydroquinone, multiply the number of moles, which is 1655.6, multiplied by 110, 182,119 grams, and then to get grams up into a higher unit value, you divide by 1,000 at 182. Probably safer to convert into grams and kilograms, because you'll get some marks for the working out if you make a mistake at a later stage. Everything is 250 kilograms is in to 3 significant figures, so I've left that to 3 significant figures here. This is to 4 significant figures, but you always take the lower number of significant figures in the data in the question. So that's the 3 significant figures, 4 significant figures, 3 significant figures is the lower number of significant figures, so I'll take that for my answer into 3 significant figures.